So today I shall continue and hopefully finish the discussion on the structure of perturbation theory on the general ground by discussing the connection between one particle irreducible diagrams and the relation with what is called the quantum effective action, which is something, an object which is a generating functional. So this is an example of a generating functional which plays a very important role in the calculation in quantum field theory and also in statistical mechanics. Okay, so I'm going to give the general definition, which is going to be a bit abstract. Then I'm going to give a very important general formula, which is the formula for this quantum effective action at first order in the H-bar expansion. It is called the semi-classical expansion, the expansion in terms of the degree in quantumness. Okay? And I'm going to show on this general relation the relation between the formal definition in terms of path integrals and the irreducible diagram. So I'm going to do an example of a calculation for the theory we are interested in, which is the phi-4 theory, which is going to illustrate this general formula. Okay? And when we have done that, I think I'll be done with this general discussion of perturbation theory in phi-4. And then I'll start, but of course, just discuss very briefly, if I have time, to discuss renormalization theory. I'll just take the Z, we are theory for massless phi-4. This is going to be continued at least one and possibly two lectures. Okay. So we have seen first yesterday that you can encode all the correlation function, the expectation value in the vacuum of products of field operator, in a generating functional which is Z of G, which is defined in a path integral formula as integral d phi exponential of minus 1 over h bar. This is the classical action we use, and then we have a g dot phi, where g is a source term. Okay, and that this object gives you a sum, well, roughly very, in a very sketchy way, this is a product of 1 over factorial n, g, the term of g to the power n, of course this is an integral, times the sum over the Green's function, g of n. This is the correlation function. And g is a source term. Okay. So that by taking functional derivative of this object with respect to g, you get the correlation functions. Okay, so this is quite a formal definition, that it makes sense if you can define properly a functional integral, and it contains in just one expression, all the correlation functions. So it's easy to manipulate. If you can make mathematical manipulation of this, we are manipulating in the same time all the correlation functions of the theory. Okay? So I claimed that out of this, we can define another generating function that's called W of G, which is just h bar times the logarithm of this Z of G. And that is, it's basically the sum over n of 1 over factorial n G to the power n times the connected correlation functions. Okay? And now we want to do the same for the irreducible diagrams, because the irreducible diagrams are simpler. There are many, many less. Okay. So we want to define an object which is a generating function for the irreducible diagram. And remember, to a given diagram, an irreducible diagram, let's call it an irreducible diagram of the phi-4 theory is a subdiagram of the phi-4 perturbative expansion, where you have, it's a subdiagram, so you have external legs, but these external legs are amputated. They are not part of the diagram of the parts. This is amputated lines. Okay, and this diagram is one line irreducible. Namely, if you cut any of its internal lines, it stays connected. Okay, and we have seen that the simplest example in the phi-4 are this diagram, this diagram, which are the simplest example of one particle irreducible subdiagrams. And we also have seen this diagram, which appear in the 6-point function. But of course, you may have a higher order diagram like this one, which is irreducible because you can cut any of the line, etc. So we want to define a generating function. Okay, so let me just write it formally. So instead of having the source term for this irreducible diagram is called the background field. And I'm going to denote it phi, this kind of phi. Okay? And that's because, in fact, it's not the same object. Mathematically, it's not the same object that the source term. And I'm going to define this quantum effective action. So let's call it quantum effective action. I defined it as some gamma of phi, which is the same thing, sum from n equal 0 to infinity. I'm going to write it more carefully, so it's going to be 1 over factorial n. G to the power n becomes phi to the power n, but this is a big integral over the endpoints dz1 and to dzn, phi of z1 up to phi of zn. Okay? And the coefficient in front of this Taylor expansion in phi is just the object that I called the irreducible function, gamma irreducible, with endpoints of z1, zn, where this is the irreducible endpoint function. That I've defined yesterday in terms of the sum of the amplitudes of the irreducible diagram with n external amputated legs. But I'm not going to rewrite it explicitly here because we are going to rewrite it, discuss it a bit later at that stage. Okay. So this is just, if you want, a combinatorial definition. This object is a formal series in G that contains all the irreducible functions. So it's just a definition. Now the question is, of course, can you compute it and define it and study it, study its property? Okay. So, because you see this, this function as a z and w have a definition in terms of a path integral. So the first important result, which is very general, a general theorem, is that gamma of phi is a mathematical object, is a Legendre transform of W of G. So we have a function of a source term W of G, and there is a general mathematical transformation applied to a large class of functions, which is called the Legendre transform. And how is defined the Legendre transform? You see, W of G is a function of G. It's a function of the function G, so it's a functional, but I'm going to just call this a function. So if W of G is a function of G, which is a function, remember, because G dot phi means integral over Ex G of x times phi of x, where phi has the random variable in the functional integral. So it represents the quantum field. By the correspondence principle, it corresponds to the field operator in the canonical formalism. So it's a function of this function g of x. Then you can define an object which is just the derivative of W of G when you make a change of the value of G at a given point x. Okay? And you see very easily from the definition of W of G, since this is h bar times log of the functional integral of Z, taking a derivative with respect to G makes that 1 phi of x gets out and is in front of the exponential. And since you take the derivative, there is on the denominator of G, so this is something which is just, well, let us rewrite it. This is d of phi, exponential of minus 1 over h bar s minus g dot phi. This is s of phi, okay, times phi of x, divided by integral d phi, exponential minus 1 over h bar s minus g dot phi with no phi. So this is just the expectation value of the field phi at the point x, but evaluated not for the theory with no source term, but for the theory where I keep the source term in the action. So let me denote this by a factor g. So this means just the vacuum expectation value of phi of x in the external field or source, in the external source G. So G is not set to 0. So the only difference between the vacuum when G is set to 0 is that we are in a different vacuum of the theory. We are in the vacuum of the theory defined with this action. So this functional derivative corresponds to the expectation value of phi in the vacuum theory of the in the vacuum of the theory where the source term is non-zero, but it's a function of x. So let me call this different phi of x. This is a standard definition. So this phi is different from this phi. Well, if you are familiar with tech, this is phi, and this is var phi. So those are two different letters in the Greek alphabets. Okay, so depending on this, I don't know, the history, the city, the highland in ancient Greece, they were using one on another. Okay. So this object will correspond to what we are going here. So this is a function. So you see, phi is a random variable, but phi is a function, classical object. But it's a function that depends on G. But it depends on G as a function. It doesn't depend only on the value of G at the point x. It depends on G, on the value of G at all points of space. So it depends on G considered as a function. So phi as a function is a functional of the function phi. So there is a mapping from the space of function G to the space of function phi, which is defined by the functional integral, but it's a mapping from function, which is non-local. Since you have a mapping, let me write it here. We have a mapping from G to phi, which is a mapping in the space of function, not in the space of numbers. Okay. So now, what is a Legendre transform? The Legendre transform here is defined simply by inverting this mapping. Assume that instead of assuming that phi is a function of G, we treat G as a function of phi. So we make a change of variable in a space of function. And we define then the Legendre transform of W. It's going to be a function of the function phi. So it's going to be a functional of the function phi. And it's simply defined by G dot this phi minus W of G. Okay? So this is a very general definition of a Legendre transform. If you have a function W of a variable G, the conjugate field phi is a derivative of W with respect to G, and the Legendre transform is a function of phi, which is defined of G, now considered as a function of phi, minus W of G. So you see, in this expression, which is a bit formal, G dot phi means the same than this. So this is G dot phi means integral over x of G of x times var phi of x. Okay, those are both functions, classical functions. But you consider that G of phi, now instead of considering that phi is a function that depends on G, I consider in this expression that G is a function that depends on the function var phi. Okay? So we make this change of variable. Okay. So this is a definition of. So you see we have two objects. We have the definition of phi as var phi as a definition of W, and then we have the definition of gamma of phi. These are the two things needed for this. Okay? So this is the definition of a Legendre transform. And with this definition in terms of transformation of functions on functional, this object phi is called the background field. Background field because it corresponds to the expectation value of the quantum field for a given theory. So in some sense, it's an average value of the quantum field that is seen by if we are coupled to the quantum field. If another particle is coupled to the quantum field in the first approximation, it is going to see the expectation value of this field as an effective or background field in which the particle lives. Okay. So this is a background field by definition. That's the name. Okay. And gamma is called the quantum effective action, as I stated. So gamma, as a function of phi, is the quantum effective action. Okay? So that's an abstract definition, but it's a very general definition. You see, in this definition, the action has not played any role. And okay. And there are some general properties. I'm going to show you some just two general properties of this Legendre transform. The first property is that, you see, if you exchange gamma and W, you can also write that W of G is G dot phi minus gamma phi. You see? So this is property 1. Okay? So W looks like the Legendre transform of gamma. Of course, this is true if we have a similar relation, which is that G of X is the functional derivative of gamma of phi when I make a variation of the background field phi at the point X. Okay. But this is true because it's an easy check that if this holds, if you take this, this is this. So var phi is a functional derivative of W, but once you define the Legendre transform, G is also the functional derivative of gamma with respect to phi. So it's a general property of Legendre transform. Okay. So, in other words, the Legendre transform of a function is in general the function itself, which means that the Legendre transform is an involution in some adequate space of function. Applying it twice, you get back to the original function. So W of G is an involution. Legendre transform is an involution, okay, in an adequate space of function. Okay, property 2 this means that when G is equal to 0, you see, when G equal to 0, it means that phi of X is just the expectation value of the quantum field phi at the point X in the theory with no source term. Okay. So this corresponds just to the expectation value of the operator phi of x in the vacuum of the original theory. Okay? So the value of, so if g equal to 0, then phi of x takes a special value, which is this. So let me denote this value phi 0. So phi 0 is the value of phi calculated by this formula when g is equal to 0. So we take the derivative with respect to g, and then we set g to 0. Okay. But then, using the fact that it's an involution, you say, what it means? What does it mean? It means that if I take the functional derivative of gamma with respect to phi at phi 0, I get 0 because g equal to 0. So this is equivalent to state that phi 0 is such that the functional derivative of gamma of phi with respect to phi at phi 0 is equal to 0. So in other words, phi 0 is an extremal, and in fact a minimum point of the effective action gamma of phi. So if you have gamma of phi, looks for the value of the background field where it gets its minimal value, its ground state, if you want. The classical ground state of gamma of phi corresponds to the expectation value of the quantum field. You see. Okay? So the classical ground state, if you want, the classical ground state of gamma of phi gives you the expectation value of a quantum field. So it gives you some information on the quantum vacuum of the theory. Okay. And property 3, that I'm not going to show, but it's simply that if you considered the second derivative of gamma of phi at two different points, phi of x1 and phi of x2, okay? Well, from my definition in here, this is going to correspond to the value of the irreducible two-point function at the point, let's call it z1 and z2. z1, z2. So it's a sum, it corresponds to the sum of irreducible two-point diagrams. Okay? From the general property of the Legendre transform, this object is considered as an operator. So you may consider this as a kernel of an operator. This is a kernel of a linear operator. This kernel is just the kernel of the inverse of the second derivative of W. Let's see, delta G of Z. So you take this. So you have a Z prime, Z double prime. So this is an operator. You take its inverse as a kernel, and you take its value at Z1 and Z2. And this object, you see, so this is the inverse of the generating function of connected two-point function. So what does this mean that this is the inverse? It means that the product of these operators times these operators is the identity. In other words, it means that gamma irreducible 2 of Z1, Z2 times the two-point function, which was denoted G2 connected of Z2, Z3. So taking the products of these two operators means this is a matrix element between Z2 and Z3. This is a matrix element of an operator between Z1 and Z2. We take the products of these two elements, so we sum over the intermediate elements. So this means that we are taking an integral over dx2. And we get delta of Z1 minus Z3, which is a matrix element of the identity. Okay, so in other words, the irreducible two-point function is the inverse of the connected two-point function. Okay? And we are going to see what this corresponds to in terms of diagrams. Yes?
When you say the kernel of linear operator, which linear operator do you have in mind?
Well, one linear operator is defined by the two-point function, connected two-point function, and one linear operator is defined by the irreducible two-point function. Remember, that's something that I wrote. If you have a kernel, if you have an operator O, which has a kernel, I'm going to write O of Z1, Z2. This means that this operator acts on functions phi of Z, let's say phi of Z1, and phi of Z, let's say. And so an operator O to a function phi gives a function, let's say, psi, which in terms of vector is O dot phi. So this function as a function is defined as the value of the point at the point Z1 is integral over dZ2, the kernel O of Z1 times Z2 times the original function at the point Z2. So you see, to any two-point function, which with adequate properties in this space, you can associate an operator O acting on functions. So this O is an operator, if you prefer, write it like that. This O is an operator. This is a function, and in terms of components in the space of function, which is the value of the function, this is so. Okay. So these operators are called trace class operator, I think. And okay, so there is a mathematical definition that you can find. You probably have studied them in the front-end lecture already. So it is just in this sense. Okay. So this is a general definition. Point one that I wanted to discuss. Okay, so now I want to show the first order general formula. So if we take a theory involving a scalar field, phi, and an action that I'm going to call S of phi, okay? So S is an action. For phi-4 theory, S of phi is integral dx, 1/2 of d mu phi squared plus m squared over 2 phi squared plus g divided by factorial 4 phi 4 of x. Okay? But I'm going to consider a general action. Okay. So this is a functional of the field phi. Okay. So you know that the classical solutions are given by the function phi such that the first derivative of S, the functional derivative of S, vanishes. Now, there is a very important object which is the second derivative of S. So the second derivative of the function S of phi is defined as delta over delta phi at a point x1. I'm sorry, well, yes, x1. Delta of phi at a point x2 of the functional S of phi. So in some sense, this is something like the classical two-point function. So it's going to be called, I'm going to denote it S double prime. So it's a function. It depends on x1 and x2. And of course, it is a functional of phi. It's a functional of phi. And it's a function of these two variables. So if you fix phi, you take the derivative, and then phi is chosen, then this is a function of 2. So it's a kernel of an operator. It's a kernel of an operator. This operator is called the Hessian operator. That I'm going to just denote S double prime. So in the sense of an operator, it's an operator like that. To an operator phi, it's associated to a function phi, it's associated a function psi, which is the convolution of phi with the Hessian operator. Okay? Okay. So this corresponds just to the second derivative of the classical action. It's an object which is well defined in calculus of variation. Okay. So for phi 4, what is this Hessian operator? So it's an operator which is a function of phi. So if we take the second derivative of this with respect to 2 phi, well, first here, we get, and for the linear term, it's a quadratic form. So it's just the operator corresponding to this quadratic form that we have already studied. So this is just minus the Laplace operator plus m squared. Okay? It's an operator acting on function. It's a differential operator. And if we take the second derivative of this with respect to phi, it takes value only if x1 and x2 are the same. And then we take the second derivative of 5 to the 4, which is 12 times phi squared. So we get g over 2 multiplication by the function phi squared. So this is the Hessian operator for the phi 4 theory. Is it clear? Okay, and to be sure, this means that if I apply this operator to a function phi, I get a function. So this is a function, let me denote this a function psi. Okay? This function psi at a point x is just the result of applying this differential operator to the function psi. So it's minus the Laplace operator with respect to the variable x plus m squared times psi of x times phi of x, the original function. plus the multiplication operator of the function phi by the big, well, var phi by the big var phi. So this is plus g over 2 times var phi of x, the function to which phi is applied, times multiplied by capital, well, phi squared of x. So you see, this phi is a function to which we apply the function, and the phi of x squared, here phi is a function at which the Hessian operator is evaluated. Okay. Good. So this is going to be important. Okay, so keep this in mind, this formula. Okay. So this is a general definition of the Hessian operator. And it's just the second derivative of phi. And this is the Hessian operator for the phi-4 theory. Okay. And of course, the Hessian operator is the operator associated to any function of several variables. So it's something that makes sense in classical calculus and not in functional calculus. I'm using it in functional calculus, but it makes sense for a function of several variables. Okay. So what do you mean by first-order general formula? Now I want to, given a given theory with a chosen action, S of phi, what is the value of the quantum effective action, which is a functional of the background function phi? Okay. Well, for a classical theory, so what we are going to do is that we are assuming that h bar is small. So we consider h bar as a small parameter, so that we can evaluate the function of z of g and w of g by using the saddle point approximation. Saddle point approximation. Okay. So if you use the saddle point approximation and you assume that h bar goes to 0, if you go to h bar goes to 0, z of g is just the exponential of the classical solution, the classical extrema of s minus g. Okay. So in this case, you can compute phi in terms of, well, var phi, the background field, in terms of finding the extrema of the action S of capital of phi minus g times phi. Okay. And then it's very easy to compute gamma of phi, because you get g dot phi minus w, which is the action minus g dot phi. So basically, you find that when h bar is 0, this is just the classical action. Okay, so there is no need to introduce a quantum action, because in the classical limit, the quantum effective action reduces to the classical action. Okay, so what's interesting is what's going on if you go to second order in h bar. So we use the saddle point approximation plus the fluctuations around the saddle point. Then you get a correction which is of order h bar, because it's a first quantum correction. And this takes a very simple form. This is just 1/2 of the log of the determinant of the Hessian operator estimated for the field configuration which is equal to the background field. And then you have higher order terms over the h bar squared. So this is the log of the determinant of the Hessian operator. Okay. So that's a very simple, compact formula. You see, it's true for any theory involving bosonic fields, in fact. So it's true for with a scalar field phi. And in fact, it's true for any theory with fields that obey the Bose-Einstein statistics. So basically, spin 0, spin 1, spin 2, etc. This kind of formula. So for spin 1 and spin 2, you have problem with gauge invariance. You have a lot of symmetries, so the formula gets more subtle. But basically, this formula is a very compact formula that you need to keep in mind. Okay. At 0 order in h bar, the effective action, the quantum effective action is just the classical action. And the first quantum correction is the log of the determinant of this. Okay? Good. So now, so there is a general proof using functional integral method of this. So this can be proven. This can be proven quite easily. The proof is in my lecture notes. But I won't have time to do that because I want to speed up a little bit. So we can go back to that if you like. But I want to see what this means for the phi-4 theory. On the example of the phi-4 theory. Well, let me just, okay. So let's see what is the consequence for the explicit calculation for the phi-4 theory. Okay, so for the phi-4 theory, the classical action is known. It has been written there. So what is the second term? What does this second term correspond to? Okay. Well, first, we are going to use a very simple formula, which is true for finite matrix. So we are going to assume that it's true for operator acting on function, which is that the log of a determinant of an operator is here S. It's just the trace of the log of the operator. And you can check on finite symmetric matrices that this formula is true, simply because you diagonal. This is a formula that doesn't depend on the basis. So if, if S is replaced by a finite dimensional matrix, if you take the diagonal matrix with eigenvalues lambda 1 up to lambda n, the determinant of this is just the log of the product of the eigenvalues. So this formula amounts to just stating that the log of the products of the lambda I, from I equal 1 to n, is just the trace of the log. So the log of a diagonal matrix is a diagonal of the log, a matrix whose matrix element are the logs of the lambdas. So this is just the sum over I to n of the log of the lambda I. So this statement just means that the log of a product is the sum of the logs. Okay. So what does this give for this? So this second term here, this one, let me represent it by a white box here. So the 1/2 is going to be treated at the end. So what is the log of that of the second? So this box here. This box. This is therefore the trace of the log of this operator minus Laplace operator plus m squared plus g over 2 multiplication by phi squared. Okay? Okay. So now we can rewrite this operator as a log of this operator, which is the Hessian for the free field theory, times a correction. And the correction is, of course, 1 minus this operator inverse times g over 2 phi squared. And I have to close this log and then the trace. Okay? I'm sorry, I'm becoming a bit messy. You see. So I've put on the left the Hessian for the theory with no coupling. Plus. I'm sorry. Thank you very much. It's a plus. Okay. And then we are going to use the fact that, well, remember, the trace of the log is the log of the determinant. So here we have the log of the determinant of this operator times this operator. But we have also the formula that the determinant of two operators, or two matrices, is a product. So even if the operator do not commute, the determinant of a product is a product of a determinant. It's a general, okay. So we can rewrite this as the log of the determinant of this times the log, well, of this times determinant of this, which is therefore the log of the determinant of this plus the log of the determinant of this, which is a trace of the log of this plus the trace of the log of this. So we get this trace of log of minus delta plus m squared plus trace of log of 1. 1 is an operator plus minus delta plus m squared minus 1 times g divided by 2 phi squared. Okay, so this is 1, and this is trace. Okay. So this is a trace of the log of the Hessian for the free theory. This is the contribution of the free theory. Okay, and this is a variation induced by the interaction theory. And you see that here you have G plus something which is proportional to G. So now we are going to do a perturbative expansion in the coupling constant G. So now I concentrate on this term. Okay. So this term is a term that comes from the free theory, let's say. Let's consider that it's a green square, and this is a violet. Okay. And let me concentrate on this term, the contribution that comes from the fact that the theory is interacting. Okay, so what I have to do is that I compute the trace of a log of 1 plus something. So I just expand log. I use the fact that log of 1 plus something is x. So log, I'm using just the fact that log of x is x minus x squared over 2 plus x3 over 3, etc. So this is going to be just the sum from k equal 1 to infinity, the term of g to the power k. And what is in front of g to the power k? There is, well, there is, of course, it's g over 2 to the power k. To the power k. There is a minus 1 to the power k minus 1 divided by k. This is the expansion of the logarithm. And then I get the trace of the operator minus delta plus m squared minus 1 times phi squared once. And then I repeat this. Up to m squared minus 1 phi squared. And this, each of these blocks are repeated k times. So you have k copies of this operator. Okay? Okay, so this is a series expansion in G for this term in the effective action. Okay, so we have a trace of products of operator. Now, let's express these operators in terms of kernels. So, what is a kernel of minus delta plus m squared minus 1? This is just the free propagator. So if you want, it's a matrix element of this operator between 2 points x1 and x2. It's a free propagator. Okay? With my notation here. What is the kernel of the operator multiplication by phi squared? It's just a delta function between x1 and x2 times the multiplication by the value of the function phi squared at the point x1, because it's just the multiplication by a function. So if we want to apply this operator to a function, we just multiply the original function by this, integrate over x2, and we get the function psi times phi squared. Okay. And so now, making products of operator means making convolution of the kernels. And taking the trace means once we have computed the kernel of this big operator, we integrate over its diagonal elements. The same. So this object is going to be simply, so let's consider the kernel between a point x1 here, for instance, here. Let's say, yeah. Well, let's say a point x0. So I consider the kernel of the operator between a point x1 and a point x2. Then the kernel of this operator between the point x2 and the point x3, etc. And I end up here with a kernel between the point xn and the point xn plus 1. But since I take the trace, this is going to be identified with x1. You see? So this object is just integral over x1, integral over x2, up to integral over xn, okay, of the kernel of this operator. So this is g0 of x1 minus x2. Then I have the diagonal element phi squared of x2 times the kernel between x2 and x3 of the inverse operator, therefore the propagator, times phi squared of x3. And I continue up to the last term, which will be the propagator of xn minus the last point that is identified with this one because I take the trace. So it's xn minus x1 times phi squared of xn plus 1, which is x1. Okay. So I have a big integral over all the points here. So finally, this big box is just sum from k equal 1 to infinity of minus 1 over k minus 1 g over 2 to the power k times 1 over k. Okay? Yes? Where is n? Oh, yes. I'm sorry. Very sorry. N is k. Yes. Thank you very much. This is k. Yes, of course. Thank you. Okay. So now, so we get an explicit expression, and we got it from this expression in terms of functional object. So now, since we have a product of propagator, we can ask what is the, this is something like a Feynman integral. It's an integral of the position of vertices of products of propagator. So what is the Feynman diagram? Diagrammatic. Representation of this object. Yes?
So what is the delta function? Why did you not include?
But the delta function has been included already in the product. If you want to be more precise, what I should have written is that I should have written that this is going from x1 to, let's say, y1. So I could have written this. Let's consider this. Minus delta plus m squared. I take a matrix element between the point x1 and the point y1. Then I take the phi squared operator between the point y1 and the point x2. And then I take minus delta plus m squared between the point x2 and the points y2. Then phi squared because the point y2 and the point x3. You see? Then what I get is that in this interval, I have to integrate over x1, y1, x2, y2. And here I have a delta of y1 minus x2 times phi squared of x2. Here I have a delta of y2 minus x3 phi squared of x3. And here I have a propagator g naught of x1 minus y1. And here I have a vector g naught of x2 minus y2. And I have to integrate over dx1, dy1, dx2, dy2, etc. So you see that as a first step, I can integrate over the y1 and y2 because it's very easy. And what remains is dx1, dx2, etc. of g0 of x1 minus y1, but y1 is x2, and phi squared of x2, etc. It's just, I just jumped over that step. Okay, so let's go back to this. What is the Feynman diagrammatic representation of this object? You see, if I represent each propagator, each g naught of x1 minus x2 by a propagator between the point x1 and the point x2, I get a chain of propagator going from x1 to x2 to x3 to x4. Okay? So I have a vertex associated to each point. x1, x2, x3, x4, xk. Okay. And to each point, to each vertex, here is a propagator. And here is just a factor phi squared of x1. Here, phi squared of x2. Phi. Okay, so I can represent it by stating that I have a truncated legs, because it's just a factor 1, but I have 2 of them. Okay. You see? And to each of them, I multiply by the value of the background field function. Okay? That's it. So you see, so I can rewrite this as this object, which is just the contribution of the one loop diagram with 2k external truncated legs. Because if you have k vertices, and to each vertices you can attach 2 internal legs and 2 external legs, okay, of the value for this diagram, this loop diagram, the irreducible amplitudes associated. So no, this diagram has 2 points. Let's say this is, you see, y1 and z1. So let's say this is z1, this is z2, this is z3, this is z4. So in fact, this external diagram has 2k external legs, but the position of the external legs are associated, are paired 1 by 1. So in fact, z1 has to be equal to z2, z3 has to be equal to z4, etc. So in fact, okay, times phi of z1 up to phi of zk, integrated over all the position from dz1 to zd to k. So you see. Okay. And this factor, so this big integral is just can be written as associated to the amplitudes of this irreducible diagram. Okay. And this factor here, well, if you walk a little bit about, this factor is just the symmetry factor for this one loop diagram. Okay? So this explicit calculation shows explicitly what I claimed at the beginning of the lecture, which is that this object defined as a Legendre transform of a generating function of connected diagram generates the one particle irreducible diagram. Because you see, this formula, this term contains, where are they written? Contains both this diagram, this diagram, this diagram. It doesn't contain this diagram because it's a diagram that contains 2 internal loops. Okay. Okay. So this formula contains all the one-loop diagram of the phi-4 series. The tadpole, just the bubble, the triangle diagram, and then the square diagram, etc., etc. It contains all of them at once. Okay. So finally, let me end this discussion by stating an important fact, which is that, and let me go there. Well, this formula, the formula that I wrote here, show that the classical theory, so the quantum effective action is given by the classical theory. The first 1 over the h bar is given correspond to the one loop diagram. And in fact, this is systematic. In fact, if we work a bit more, you see that the term of order h bar to the power, let's call this b, in the expansion of gamma phi correspond to the irreducible B loop diagram. So for instance, this diagram, well, which is the diagram that I wrote here, this one, or this one, okay, or so this is a two-leg diagrams, or if you, but you can also consider this one, which is a I'm sorry, there's only one. You see, these are two loops diagram with 4 external legs, 4 points. This is a two-loop diagram with 6 external legs, so it's a 6-point irreducible diagram. They appear at order h bar squared. And, well, you can prove it by using this kind of generalization of calculus, but you can just prove this by counting the factor of h bar that comes from in the perturbative expansion of, for instance, irreducible function. Simply think about the connected functions. The connected functions. Connected functions. If you consider a connected diagram like that, remember, you have a factor 1 over h bar per vertex, internal vertex. You have a factor h bar per propagator per vertex, okay? And you have a global h bar factors per connected component. Because in the definition of W here, we have added an h bar. Okay, so the total weight of any diagram is h bar to the power the number of lines minus the number of vertices plus 1. You see? And here, for a diagram like that, you have 1, 2, 3, 4 lines, 3 vertices, plus 1 means 2 loop. Okay. And you can check. And this number, the fact that when you have a general graph, the number of lines of the graph minus the vertices of the graph plus the number of connected components of the graph is equal to an object called the number of loops of the graph. This is equal to the number of internal loops, but in mathematics this is known as the first Betti number, I think. So it's a formula that goes back to Euler, the famous mathematician at the end of the 18th century, which was this, that's basically the formula that gave the birth to the field of mathematics called topology. This was the first example of a topological formula. And it's associated to the famous problem of the bridges of cities that at that time was called Königsberg. Bridges problem. Okay, so the semi-classical expansion in H bar is called often the loop expansion in theoretical physics, because it's an expansion is a number of loops of diagram. And that's very general. It's not restricted to phi-4. It comes out everywhere. It's true from quantum electrodynamics. It's true for gauge theories. It's true for gravity, quantum gravity, perturbative quantum, etc. So it's a general, very general feature. Okay. Okay, so now let me, I might do this. Let me start. I have 10 minutes left. So I think the best is just to start to discuss now the problem of renormalization. So up to now, I've been studying the combinatorics of perturbation theory. So we haven't really done any physics yet, except that now we have some way to compute the property of the vacuum of the theory through the effective action. So now, this was introduction. And you heard about renormalization already in the QFT1 course and in a different framework, but the math are in fact very similar in the statistical mechanics course. And in quantum field theory, this problem is very important for several reasons, but one reason is that in perturbation theory, we have ultraviolet singularities, or divergences, which means that all the objects that I've been discussing here are, all those integrals are ill-defined because of short distance divergence, unless we use what's called an ultraviolet regulator. So we modify the theory at short distance in order for it to be well defined. And for instance, one solution is to put it on a lattice. Another solution is to introduce some momentum scale so that all the momenta are supposed to be less than some maximal momenta lambda, some big energy scale. That's two examples of modification of the theory. Okay, which if we introduce that, for instance, the functional integral makes sense, but we lose some interesting properties of the theory. For instance, on a lattice, of course, you lose Euclidean or Poincare invariance, which is quite bad. And here, in fact, you lose unitarity. So you have problem with Poincaré, with unitarity, etc., and causality, etc. Okay. And so the issue is, can we construct a theory where this ultraviolet regularization, if it's introduced as an intermediate step, can it disappear? Can we get it? Okay, so can we introduce a regulator? This defines the theory. And then can we get rid of it to get a consistent theory? Okay, so the main property of a quantum theory is that when you define a theory with an ultraviolet regulator, you are not defining the theory in terms of the physical observable of the theory. So there is a difference between what's called the renormalized parameters, which correspond to observable quantities, okay, and what is often called the bare parameters, although I don't like very much this, which are the parameters that are needed in order to construct a regularized theory. And in 5 minutes, I can only explain on one very simple example the difference between bare and renormalized parameter. And I'm going to consider the two-point function. Irreducible two-point function. We have seen that the two-point function, the irreducible two-point function is this diagram, but this is a truncated line, you see. This is a doubly truncated line, plus G 1/2 times this diagram. So this is what plus, and there is a factor h bar, as we have seen, but okay, let me forget about the h bar. So this is a two-point function, irreducible, as a function of the 2 points Z1 and Z2. Okay. Here's a point 1, here is a point 2. 1 and 2. Okay. Well, as usual, especially if you are interested in high energy physics, you go in momentum space, so you take the Fourier transform of this object. So with respect to the 2 points, it's a function of 2 momenta, but because of translation invariance, there is a 2 pi to the power d times delta of P1 plus P2, if P1 and P2 are the momentum, so it depends. And it's an object that depends only of one momenta, P1, okay? So I'm going to call the irreducible function with hat, because it's a Fourier transform of just one momenta. It's a momenta that goes through P1, and P2 is the opposite momenta. This is just the law of conservation of momenta. Gamma 2 of P1 is of P. So this is the inverse of the propagator. So this is P squared plus M squared. And then I get the factor G divided by 2 times the amplitudes of this diagram that I'm going to call T of M. So T of M is the amplitudes of the tadpole diagram. Therefore, this is integral over some internal momenta, d dk over 2 pi to the power d, 1 over k squared plus m squared. Okay? And this integral, as we have seen, is ultraviolet divergent. So if we integrate a momentum cutoff, k less than lambda, so I introduce a sharp momentum cutoff, okay? This is finite. So I integral for the momenta inside a ball of radius lambda, with lambda much larger than m, because m is what we would have expected to be a physical mass. Then, of course, this is a function of m and of lambda. So for the moment, think of it as a function of t of m and of lambda. Okay, we are going to discuss it tomorrow. Okay? And then we get terms of order g squared. Okay. And in this calculation, I set h bar equal 1. Because as we have seen, making a perturbation theory in G is the same as making a perturbation theory in H bar. This graph comes as G H bar, and the term of order G square will be 2 loop diagrams, so it will be a G H bar square term. Okay, so I set H bar to 0 for simplicity. Okay, so now remember one of the results I stated and that I erased, of course, is that, no, it's here. It is that the irreducible two-point function is the inverse of the connected two-point function. So this means that the propagator of the phi-4 theory, so this is the two-point connected functions. If I consider its Fourier transform, it's just 1 over gamma hat 2 point of p. Because it's a function which is diagonal, and this is a function which is diagonal in momentum space, the inversion of operator becomes just the inversion of the function. Okay. So this is 1 over p squared plus this term. Okay. So let me call this m squared, capital M squared. Okay. So we have m squared equal m squared plus g over 2, this function of parameter m and of lambda. Okay. So what is this m, this capital M? This is just the mass of the one particle state of phi-4 theory. And this comes just from the Chelan-Lehmann representation theorem. I'm not sure Kalen. Is it written like that, or is the H somewhere else? No, there are 2 L, I think. Is this? Yeah, okay. It tells that the first pole in P squared corresponds to the mass, the first excited state. And here we have P squared plus M squared because we are in Euclidean space. Euclidean space. So remember, if you go to real space, what I call P squared is minus K naught squared plus K vex squared in Minkowski. So a pole at P squared equal minus M squared means that the energy of the particle is square root of the mass squared plus the momentum, which is a dispersion relation for a particle. Okay. So this is a mass. This is the physical mass. That's something that you measure. If you take one quanta of the field and put it on a scale, yes, that's how much it weighs. Okay, so this is a physical mass. Okay, and m is just a parameter in the action we started from. So you see that there is radiative corrections. What's called radiative corrections to the mass, and that's an effect that I'm sure you have started to study in QED, because in QED that's exactly the same. There is the same phenomena. The electron gets a radiative correction to its mass through interactions with the photons. So basically, this kind of Feynman diagram in QED, where you have a virtual photon which is emitted and then absorbed by the electron, gets a radiative correction to the mass. So that's exactly the same effect here, except that here we have a self-interacting boson. So what's happening is that the boson emits a virtual bosons, and then interacts with it immediately, but still it propagates in space-time. So this is the same phenomena exactly for QED and for bosons, scalar bosons. Okay, so this parameter is not the physical mass. And what we are interested in constructing a theory which has a given physical mass. So in other words, in terms of the Baire parameter, the physical parameter gets renormalized. Or if you want to construct a theory with a given physical mass, you have to construct your path integral, your quantum theory through a path integral. In my case, I'm interested in path integral, by being very careful on what are the parameters g and m in the path integral compared to the physical parameter of the series that I'm measuring in an experiment, like the mass and later on the coupling constant. So that's what we are going to do tomorrow. So this was just an introduction. We are going to discuss renormalization tomorrow. And if I spend some time in explaining this quantum effective action stuff, one of the reasons is that dealing with it makes the discussion quite easy in renormalization. But that's not the only reason. It's because effective action is very important in discussing, for instance, pattern of symmetry breaking in early universe or things like that. Okay, thank you.